presentation.
Yeah. I just shared in the chat there that we'll have speakers from Touch Éireann, OSNI, NPWS, Med Éireann and Google coming up at other meetings. So
I'm trying just to put this presentation in a presentation mode. Yeah, can you see it?
Perfect.
Right, perfect. So hi everyone, my name is Olbert. I am a lecturer in civil engineering at University of Galway, and I am a PI mostly working in the area of numerical modeling. So numerical modeling, it's my first love, except my husband, he might be not happy hearing this. So yeah, academically research, it's numerical modeling, hydrodynamics for the last 20 years, modeling, and then later expanding to water quality, that is very relevant to sediment. So definitely a numerical modeler by trade, by interest. But somehow how research life works in Ireland, you need to go into a bit different areas to make sense of your numerical model or just find its application. And so the last few years, we're doing a lot of work in machine learning. And just very recently, trying to use Earth observation to kind of inform our results, to understanding of what's coming out from the numerical model. So I'm based at the university. I have established and lead a really interesting group of researchers. We are called Eco-Hydroinformatics Research Group. We are a bunch of 11 people, 6 postdocs and 5 PhD students working in various areas related to numerical modeling. So I don't really have a few slides on my CV as Jeanette did, and I must say I'm kind of quite envy of all the journeys you took. You know, you've traveled to different countries for postdocs, and then you work in different companies. So my CV is quite boring. I've done my PhD in civil engineering at University of Galway. I've done my few years of postdocs, and then I moved to the lectureship. So, and that's where I am, and that's where I'm very comfortable with. Right, so that's a little bit about me. I need to give a credit to all the people you see here on this listing, because that's pretty much, this work has been done really by them. So I'm gonna cover over the next 25 minutes or so, but I hope not to go too long. And I'm going to cover 2 projects that I am a PI of, and they both use a bit of Earth observation. So I won't be really talking a lot about all the different aspects, and kind of try to rather focus on that could be of most relevant and interest to you, which is Earth observation. So Stop Floods, it's the first project. It's about flooding, and it was interesting to see what Sinead had to say. We kind of work in a similar area. And the second project is AquaCop, funded by EPA, and that's about water quality. Again, very relevant to what Sinead was talking about. I never knew that there is so much linkage between ourselves. So we might catch up after really this event. So let me just move. Right. So Stop Flood Projects, it's a SF500 project that really aimed to develop a system and methodology for flood forecasting. And this is not really a trivial thing, because floods can be quite complex. In many areas, they're compound, and compound means that we have coastal and fluvial signals occurring simultaneously. And so forecasting of this event, it's not easy at all. So we have developed a kind of 3-step model that includes statistical, hydrodynamic, and machine learning modeling. And in recent times, the last really few months, we moved a bit to Earth observation, which will be probably the main focal point for today. So I don't really need to tell you how costly and devastating floods can be. And in Ireland, there are over 300 communities being subject regularly to floods. And we really don't need to look far back to see some really devastating flood events. So September, dam break in Libya, killing thousands of people. October 2023 in Middletown, we've seen all the images. Coastal, well, mostly fluvial, pluvial floods. And more recently, in where I am now based in Galway, flooding over Galway County. And here is the image from Salt Hill in November 2023. And really, as a civil engineer, I know that we need to build flood defense systems, but it's not really everything. We can't build walls everywhere for everyone. But what we can do, we can build really a good, reliable flood forecasting system. And this is not really a trivial job because floods are complex and floods are compound. So just to give you a little bit of flavor before we go to this area observation on what actually compound floods are. So these are those events driven by a particular storm, and storm might generate high river discharge and high seawater levels. And when the two signals occur, we might get a compound flood. And we do quite much of those in Ireland on Irish coast. And that really motivated my work. So here I'm gonna show you a little bit video. I hope you can see it. That's really a hydrodynamic model of flooding in Cork, rural and Cork City, that is driven both by the fluvial driver and by the coastal drivers. And you can see the propagation. It clearly shows that when the both waves, fluvial and sea level interact, we see quite devastating flooding. And this is a simulation from really the most severe flooding kind of modern history of Cork City. That was 2009 event. So before we go to how we apply this area observation, I want to give you a little bit of background to all this flood forecasting, and I hope you don't mind. I hope you find it somehow interesting without giving too much detail. So this is really a three-step approach, and the really main result is to find a reliable machine learning model that can be used for flood forecasting. But really, to have this reliable machine learning model, we need to do a bit of statistics, a little bit of, well, a lot of hydrodynamic modeling, and a little bit of information from Earth observation. So I'm not really gonna now go through all the statistics. That's no point here, not scope for today. But important is that we need to do some complex turn probability of occurrence of different flood drivers. And at the end of the day, what we're mostly interested in, I hope you can see my cursor, are those curves, cupolas, those curves of joint probabilities of flood occurring due to high river discharge and high seawater level. And this is the information then hydrodynamic model takes. And so later hydrodynamic model can be used for forecasting. So the hydrodynamic model, the one that we use, it quite complex setup, is trying to downscale from ocean scale conditions through mesoscale into a very high resolution model of Cork City, which is developed for all the flood inundation modeling purpose. So that's the setup. I won't be telling you more about that. It's not about today. And this is the validation of the model. Important is just to look at the middle picture and see, well, the model is performing well. So this is the model results compared against the polygons from OPW. So we have a model that we have a good confidence in. So now having the model, we can do a lot of different studies, looking at the fluvial floods, coastal, most importantly, looking at the coastal fluvial events. And this is all great. We've learned a lot from it. However, there is one big problem with the model, as most of the model I'm aware of. They're extremely slow. They run slow, they're very expensive computationally. So which means we can't really use them for operational forecasting. But what we can do, we can use this model results now to train the machine learning algorithm, the machine learning network. So we've ran loads of different events using hydrodynamic model. So that can be used now to train, to validate and test the machine learning model. And again, we've run different algorithms. I'm not gonna talk about them. It's not the scope for today. But the thing is that we can have a good performing, robust machine learning model. And I think we've demonstrated this. We've done a lot of stats to confirm that, you know, one particular model here, it's working very well. So we can now use the system to forecast floods. So really by that, we can, if we know what's coming in down the river in terms of river discharge, and if we know what sea level it's occurring in Cork Harbour, we can say if the city particular pixel 2 by 2 meter, will it be flooded or not? And if it will be flooded, what will be water depth? So this was all the introduction to flood forecasting. I hope you wouldn't mind to hear a little bit about that. And that's really where the Earth observation comes in. So we have a good machine learning model. However, if we put a lot of information into this model, it will produce better results, right? If we train it well, validate it, then it can serve the purpose better later. And we have noticed, and it's actually similar to observation to what Jeanette was saying, that we don't have many records of past historical flood event for Cork. And there is really no one's fault. It's just between different departments, agencies, kind of this information has been lost. So as Jeanette got the request from OPW, trying to trace all the historical events, that's where we use observation, and we're trying to trace all the past events. So if we know the past events, when they happened, what was the scale detection of flood, you know, what was the area, we can build around this hydrodynamic model and then use it later for validation of our machine learning model. So it seems like all these problems are all across different departments and agencies. So observation seems to be a tool for us really to find all the historical flood events for Cork. And, you know, in general, for monitoring of floods, there is a lot of different relevant satellites, but for us, at least for the last number of years, Sentinel-1, SAR data gives us the best option really for older than 2014. We've used Landsat with a very, I would say, very average result. So when it comes to flood detection, for us, it's Sentinel-1 and Landsat. Who knows, we might be going more into flood forecasting using Earth observation and all the satellite that might product products around precipitation and soil moisture would be also very useful. And you know, I'm sure in this community, you know everything about Sentinel-1 and SAR and how it's operated. And so I don't really need to go into the space and really repeat what all I'm sure you already know. But pretty much what we're trying to do with the SAR data sets that we obtain, you know, loaded into Google Earth Engine and start trace back all the historical events. So that's really how it works. It's a really standard code where we just put kind of mostly in the kind of semi-automated manner all different time frames, trying to trace as far as we can. 2014 with Sentinel, the VH band, that's the one that we use because we mostly work in the rural area, which seems to be kind of working best. We've kind of implemented different filters to remove the speckle filters to remove all the noise, the individual noisy pixels. There's always an issue with thresholds, you know it yourself, and it's a good to have some control points, some observations that you can really validate your solution. And that's not really easy because most of these events in the rural areas, they haven't been well archived. So we don't have those results, but we do have a hydrodynamic model, which was validated in the past. So what I'm trying to do here, what I'm showing in the top figure, it's a map of Cork City and in general a bit of Cork County. So the rural area to the west and Cork City, really down city center in the middle. And below that you have actually a SAR image, a scene of Storm Babette, which happened in October 2022. And so we don't have any images of what actually happened in terms of the flood extent in rural area, but we do have a hydrodynamic model, so we can kind of sense if the images, scenes, and hydrodynamic model are similar. So both for the rural area and both for the green park, Fitzgerald's Park in Cork City, it's showing really the same flood extent, which is really good. So really the purpose of this whole exercise with this area of observation here was to find as many past events as we can for Cork. And so you have Storm Babette on the top, then it was a large flood event in February of 2021, then it's October 2016. And so we found around 10 or 12 events that were relevant, and this information we can now use to really provide information for a hydrodynamic model, for its validation. Then we can use this information for training of the machine learning model, which is our forecast model. And then we can also use it for validation of the machine learning model. So this is really kind of complex, and I'm aware of it. But Earth observation definitely, SAR images of the detect flood are very, very useful for us in this area. So we mostly focus on rural area and river discharges. The next step for us is to go and look more into city center. So that's more complex because of the double bands, because of the resolution of the pixel, because of a highly dense city center, which most of the pixel would have some amalgamation of wetting and drying. And also because tides, which we mostly see in the city center as a kind of driver of flooding, come in and out very quickly. So tides change, every 12 hours, rising 6 hours and falling within 6 hours. So remote sensing and satellite observation with the revisit time are not really very helpful for those tidal events, but are quite good for fluvial events. So I'm gonna leave this whole flood forecasting research now, and I hope I gave you some flavor in what we've been trying to do in that space. And I move on to another project that we work in the last 8 or 9 months. So this is a project called Aquacop. I'm a PI of this project, and it's been funded by EPA. And what we've been trying to do here is to assess water quality in transitional and coastal waters using in situ and using Copernicus product. So there's a group of people working here, Jalal Uddin, who's a postdoctoral researcher, a main driver of this research. Diganta, Sajib, I'll mention their name as I'll be going through results, so you can kind of see, how wonderful work those people have done. We have some people, experts from outside of our organization, of our group. And yeah, so let me just go a little bit to that space without not giving too much background. I'm very cautious of time. So we all very aware of the fact that water quality of surface water just deteriorates all the time in terms of improving, and just over 30% of transitional water meet the good or high status. It's a little bit better for coastal for a reason. 80% of coastal waters are at high or good status. It's still really not enough as given by Water Framework Directive. So EPA is really very keen to take some measures, but first of all, to have a good, reliable monitoring system in place. And and as a complementary to in-situ observations, they would also like to use satellite products. So there are really three aims in this project. One is just to assess the accuracy of all the available products for water quality assessment, and to generate, if we can, some optically active and inactive indicators, and then from this information build a good water quality model that can be used for assessment of water quality in Ireland for transitional and coastal waters. So I'm going to present a bit of work of our students now. I hope not to go too much into detail. So our case study is Cork. EPA takes around 32, selected 32 location sites for sampling, for monitoring, those that would be suitable for a comparison with remote sensing products. There are only 11 sites, as you can see them in the green dots. And really for water quality, we need to collect number of indicators, parameters, and looking at them from the satellite products, we can divide it into optically active and those optically inactive. So those that we can retrieve from observations is chlorophyll, TSM, CDOM, also salinity, sea surface temperature, and turbidity. So these are the products that are available. However, there are a number of products that are not available, but we do need them for assessment. And if you think of phosphorus, nitrogen, EOD, COD. So what I'm going to do now, I'm gonna give you a little bit of flavor of what we do in terms of chlorophyll retrieval, and what we do, how we can estimate dissolved oxygen as an optically inactive water quality indicator from satellite data.
So you just have 5 minutes, Indy.
Okay, so I'll just run through it very quickly. So Mir Diganta, who is a PhD student, is doing fabulous work on trying to compare results from different chlorophyll A empirical algorithm, and he selects 18 of those. And apologies for throwing you all of this information here. I know it's not a good manner, but if this presentation is available, each of you, if you want to download it, you can have a look to yourself. Really, I'm not going to discuss it in detail, except that Diganta has used those empirical algorithms and compared them. They retrieved chlorophyll A with in situ information, and he wasn't necessarily happy with that, with the results, and I'll show you in a moment what we got for Cork. But in the late research, what he decided to do, he decided to tune all the coefficients that are in those empirical algorithms. Some of the algorithms are complex, some of the algorithms are quite simple. And so what he has then done is compare how the algorithm can be improved by tuning coefficients. There is still some work to do on that. It's really site-specific and even kind of specifics to given a temporal scale. But what I'm trying only to tell you that certain algorithms produce, when they're tuned, produce some kind of decent results with good correlation. So perhaps there is a way of finally getting a good algorithm and retrieval mechanism for chlorophyll in transitional and coastal waters. If you look a little bit statistics, again, I won't be going through in detail through that. It kind of shows that chlorophyll can be retrieved. We're not necessarily fully happy with those results. And so what Diganta has done now, as always using machine learning, he developed 600 of different combinations of different spectral bands, and what he's trying to do, come up with the new empirical algorithm for retrieval of chlorophyll A. and that we hope will be quite universal and might work really well for at least for Irish coastal waters. So maybe at some point in time next year or 2 years time, I'll be happy to report on that. But anyway, even in the form as he retrieved chlorophyll A, it shows quite good application. And so we can assess trophic status. And again, I don't really want to go too much in detail into it. However, remote sensing chlorophyll A, remotely sensed chlorophyll A, it's working for assessment of trophic status. So I think I'll leave it there. If there's some question, I'm happy to answer them, because I really want to spend a minute and talk a little bit on our recent developments, how we are estimating dissolved oxygen from Sentinel-3 level 1 data. So that's not really trivial. We know it. They are optically inactive. And so now Majid is another student of ourselves that works with our postdoc, Jalal. And they look at correlations between dissolved oxygen. So this is really a lower part of this graph against 11 of the Sentinel-3 bands. It's just was a preliminary study just to really get the sense of relationship between dissolved oxygen and those different reflectance from different bands. And what he has done in the next step used machine learning. As you will see, we use a lot of machine learning for a lot of different applications. And he was trying to predict dissolved oxygen from those 11 bands. And here we're showing a comparison between the actual in situ dissolved oxygen and against machine learning and remotely sensed dissolved oxygen. So again, it's a bit limited study in the sense that we might argue and ask many questions why we choose those 11. And there was the preliminary study. One particular machine learning model worked very well, and the correlation is high. However, what Majid is doing now is looking specifically at different bands, at different spectral bands. So try and use machine learning to detect certain features that might be correlated in relationship with dissolved oxygen. So I'm not presenting this work here because it's in progress, but it's showing some promising results. So he is working on 3,000 different combinations of machine learning models, and we hope that he can obtain some very interesting results. That there is a possibility of retrieval of dissolved oxygen from reflectance. So that's pretty much, I won't be going through all the details, but just at the end, just the map from the initial study he had done. On the left, it's an interpolated map of in situ dissolved oxygen. On the right, there is an interpolated map of dissolved oxygen obtained from those 11 spectral bands. So it shows really good comparison as a good start point. I think it's working quite well, but there is still a lot of work that we can do in that space. So apologies if it took me a little bit too long. It's just 2 o'clock now. Yeah. So I think I finished here. So present a bit on flats. At some point, I'll be happy to come back and show you more studies, and the same on water quality. And I found very interesting how our work and the work of Sinead is actually kind of nearly overlapping. And there's a lot of complementary work between ourselves. So thank you very much for your attention. And I hope I didn't really rush too much with that, and I didn't flood you with information.
Thanks very much indeed. That was great. Just a very quick question, because we are over the time now. Is there any possibility for not involving a mathematical model, but